Okay, the next network model that we will be discussing is called the shortest path model. Okay, and let me give you quickly 5 seconds to read the base problem that we will be dealing with. So this example talks about the same graph as with the example we used in the minimum spanning tree. However, we will be changing some of the numbers. So what I have here are again 7 cities, city O, A, B, C, D, and D, E, and T. In this case, we still have all the edges here represented by these lines, and the numbers are again distances. Okay. Now, because this is a shortest path problem, then the problem now talks about looking for the shortest path from O, and this is O because this is your origin, okay? Origin. Shortest path from the origin to the what we call destination, okay? Destination node. So what we have here is a shortest path problem. Now, the algorithm that we will be discussing or using to solve the shortest path problem is called the Dijkstra's algorithm. The Dijkstra's algorithm is a one-to-all algorithm. Now, before I define what one-to-all means, do know that there are three kinds of algorithms for shortest path problems. No? What are the three kinds of algorithm? One is called one-to-one, the other one is called one-to-all, and the last one is called all-to-all. Now, what do these terminologies mean? What is one-to-one? An algorithm is a one-to-one algorithm if the algorithm is able to show you the shortest path from one single node, no, from one single node to one destination node. So if an algorithm is one-to-one, then you can only get the shortest path from one origin and one destination. Okay? One origin, one destination. On the other hand, if your algorithm is a one-to-all, then this means you set one node to be the origin and you can look for the shortest path from this particular origin to all the other nodes, no, as your destinations. And I hope this is clear that if an algorithm is all to all, then you can set all nodes to be your origin and all nodes also to be your destination. Now, one-to-one algorithms are usually fast to implement. All-to-all algorithms are usually it takes time to implement, no? Because you're looking for all the shortest path from all nodes to all the other nodes, and that is nice compromise in between are one-to-all algorithms. And in this case, the Dijkstra's algorithm, one of the most popular algorithm in network models in the shortest path problem, the Dijkstra's algorithm is a one-to-all algorithm. Now, in order to discuss and understand the Dijkstra's algorithm, let me define some terminologies first. Okay? Now, whenever I use the term u or the variable u or the notation u sub I, no? U sub I will denote the shortest distance from source node, from whatever source node, in this case, the source node is generically node 1, no, up to node I. And that is your I here, the subscript I under U. Okay? So if we are talking about, let's say, U sub, let's say, D, this is the shortest distance from whatever the origin is, from the origin to node D. Okay? Next, the next terminal notation is D sub ij. And D sub ij is simply the length of arc ij. Whether it's arc or edge, no? Whether ang edge. Obviously, if the connection is an arc, then we know it's a one-way. If the connection is an edge, then it's a two-way. Okay? Finally, the Dijkstra's algorithm is a labeling. No? This is a labeling algorithm. What do we mean by that? When an algorithm is a labeling algorithm, then your nodes will be labeled. And in this case, how will your nodes be labeled? Your nodes will be labeled this way. No? Its corresponding U sub j, or the corresponding U, comma, a certain I. Okay? Now, for us to understand what U sub j, comma, I means, let us say, let's go back to this example, and let us say we are labeling node B. Okay? For node B, the label is 3C. And what do we mean by a label of 3, C for node B? This means that 3 is the shortest distance, no, from origin. And in this case, let's assume that the origin is node O to node B. Okay? And in order for us to get the shortest distance of 3 going from the origin to node B, we have to pass through or go through C. Okay? Which means this edge is included. In fact, this distance of 3 is this path. Okay? Now, let me show you another possible label for node B, no? So that you won't be confused later. Well, I will be confusing you now, but hopefully later on you will understand why. For example, I will use node B again, no? And the label here can be for A. It is confusing right now because as we defined U, where is the definition of U here? No, if our definition of U is the shortest distance. So how can the label of B be 4 if in fact 3 in fact is the shortest? This path is the shortest from the origin to B. Now, let me confuse you by saying that the 4 here, or the definition of the shortest distance here, lacks a certain condition. And what is that condition? Let me insert the condition so far, or as of now. What do we mean by this? So far, as of now. Given this label of 4A, this path is actually this is what the label 4A is representing. The path from O, no, from O to A, and then A to B, with a total distance of 2 plus 2 equals 4. And how can 4 be the shortest distance? No? 4 can be the shortest distance as of now or so far if we haven't seen this, no? This path. It is very possible later on when we apply the algorithm that we haven't seen this path. And therefore, it is very possible for node B, no, node B to be labeled with the 4, comma A. Because eventually, when we see this path 3C, then this will get updated, no? Updated meaning replaced by the label 3C eventually. Okay? So maybe a better definition of U sub I is the shortest distance as of now or so far from source node 1 to node I. Now, when we give a node a label, these labels can either be temporary or permanent. Now, a label is temporary if it's not permanent. Okay? I think that's obvious. So let me define first what a permanent label is. A permanent label is a label that we are that is deemed to be the best already. Meaning you are sure that that permanent label or that label with the distance U sub I is the shortest. It's already the best. No? It's already the best. Now, if you are not yet sure that the distance or the label is the best, then obviously that label is still temporary. And if the label is temporary, then it can be replaced by a better label or eventually become permanent if we are eventually sure that that label is already the best. Now, we need to understand temporary and permanent labels because the algorithm of Dijkstra's involves 3 steps, no? Step 0, step I sub A, and step I sub B. And this algorithm involves labeling your nodes either with temporary labels or permanent labels. Okay? So the next 2 slides will uh, give you the algorithm. However, for us to easily understand the algorithm, okay, let me convert these 3 steps into a pseudocode again, no? So that it will be easier for us to understand how the algorithm works. Okay? So let me go through the different steps first of the main algorithm. So step 0, or essentially what we call initialization. So in the initialization step, we will label our source node or the origin, okay? No? Source node 0 or the origin with the permanent label 0 dash. Now let's try to understand why the label is a 0 dash. Because this is the label of the origin, therefore 0 is the shortest distance from the origin to the node. And what node are we talking about here? We are talking about the origin. Therefore, the shortest distance from origin to origin obviously is a 0. And what node do you have to pass through to get this distance of 0? Nothing. Okay? And that is why the label is a 0 dash. And then you set whatever you set an index I to be equal to 0. Okay? Or in this case, the origin. Now, step 0, step origin. What you will do is you compute for temporary label this for each node j that can be reached from node I, provided that j is not permanently labeled, or in this case, temporarily labeled. If j is already labeled with some other label through another node k, and if you reach this condition or you meet this condition, then you replace the labels. Okay, and this is what we've been talking about here. No, this is currently the label for node B, but if we find a different label where 3 is lower than 4, the new distance we found is lower than the current lowest distance we found, then we will replace. We will replace. Okay? After doing step I sub A, we do step I sub B. What does step I sub B entail? We check if all nodes are permanently labeled. Because if all nodes have permanent labels, then we stop. So this is our stopping condition for the algorithm. Otherwise, we do this. No? We look for the u sub n with u. Essentially, we look for the label with the shortest distance u sub n. And we make it as permanent. And we just repeat the algorithm. Now, the next two slides will contain the pseudocode for the Dijkstra's algorithm. Okay, so again, step 0, initialization. We set the origin as the current node, and we set I to be the origin node. So I, in this case, is your current node. Kung nasaan tayo ngayon. Okay? Now, for step I, sub A, no, what do we do? For every temporary node that is directly connected to the current node, so wherever we are currently, for every temporary node that is directly connected, no, to us, if the node is labeled, then we compute for this. No? Because the node is labeled, then we can give it a temporary label. However, if node is labeled, no, then we compare the current node with, we compare the current label with the temporary label u sub I plus dij comma I. And whichever is smaller, we will give it, no, to the current node. Step I sub B, if all nodes are permanent, then we stop. Otherwise, we select the temporary node with the lowest distance u sub n, then set that node as permanent and the current node. Now, let me apply the Dijkstra's algorithm in our example. No? And at this point, it will be nice if you are able to keep track of the algorithm, because it will be very hard for me to keep on switching back and forth from my notepad or from my notebook to the algorithm. Okay, so I hope you keep a copy of the algorithm beside you. Now, the very first step of the Dijkstra's algorithm is to label the origin, and we'll put the origin O with the label, remember, 0 dash. And according to step 0, no, we will give this label a permanent status. So let me put status here, and I'll just put P, so that it will be noted as permanent. Now, and if you remember, I now is set to be the origin. Okay. Now, the next step, requires us to look for all the nodes that are directly connected to our current node. And our current node is O. And as you can see in this graph, nodes A, B, and C are the nodes that are directly connected. So you have OA, you have OB, and OC. So A, B, and C are directly connected to node O. And because A, B, and C are not currently labeled, then we will just give it a label. Okay? So node A, B, and C. Now, what is the label for node A? The label for node A, no, according to the algorithm, is a U sub O plus D sub O A, comma, O. And what is this equal to? This is equal to U sub O is the shortest distance, is the distance of the shortest path from the origin O to node O, and that is this. So that is 0. Okay? Plus, what is DOA? DOA is the distance from O to A, and that is 2. And, comma, we have O. Okay? So this is 0. So, sorry, let me put a slash to, so that it will represent a 0 and not an O. Therefore, the label for node A is actually a 2, comma, O. What is the label for node B? Again, using this label, it is a U sub O plus D O B, comma, O. And this is equal to, again, 0 plus 5. Why 5? Because that's the distance from O to B, comma, O. Therefore, this is a 5O. And finally, what is node C? What is the label for node C? Node C is U sub O plus DOC, comma, O, which is equal to 0 plus 2, comma, O. Therefore, this is a 2, comma, O. Okay? So let me erase these intermediary equations and just retain our final label. Okay? So the final label for A is a 2O. For B, it is a 5O. And C is also a 2O. Okay, so let me erase this. I'm sorry. Okay. Now, the next step requires us to look for all the temporary nodes, or the nodes that are that have temporary labels, and look for the smallest. Because 2 is the smallest among all the distances of temporary labels, therefore we can actually set either A or C to be the next current node. And in this case, the algorithm does not give us any tiebreaker, no, a way to break the tie, and therefore we can actually what they call this? We can actually arbitrarily choose between A and C. Okay, so let's say, just for the sake of the example, let's say we make A our permanent, no? So we make A our permanent, and as part of making A our permanent node, we replace our current node. Instead of our current node to be O, we are now at A, node A. Okay? And then we just repeat step I, or in this case, step A. Now, in step A sub A, we look for all the nodes that are directly connected to node A, to the current node. And these are O, B, D, and T. However, because O is permanently labeled, okay, because O is permanently labeled, then we will not look at that connection anymore. Because we've already found the shortest distance or the shortest path, no, from origin to O. Therefore, we will not look at that anymore. Therefore, we will only be labeling or updating our labels for node B, node D, and node T. Okay? Now, because node D and node T are not yet in the table, then we will give it a label. So let's put D here and T. And because node D and T are not yet labeled, then we can easily compute for the label here. And if you remember, the label is U sub I. What is I right now? U sub A plus the distance from A to D. No, sorry. Comma, sorry, it doesn't want to erase, comma, A. Okay? And this one is equal to, what is your U sub A? U sub A, you go to node A and the distance is 2. Okay, 2 plus, what is the distance between A and D? A and D is 7. Okay, so 2 plus 7 is 9. And you have to go through A. What is the label for node T? Node T is U sub A plus D A T. So that is a 2 plus distance between A and T is 10. So that is a 12 A. So I just cleaned up my labels for D and T. We have the label 9A for D and 12A for T. Now, that is for nodes D and nodes T. These nodes are the ones that are newly labeled. What about B? B is currently labeled with a label of 5O, but we need to check if there is a better label for it. Now, for B, and let me write that here, okay? For B, the label going through the current node A, no, should be U sub A plus the distance from A to B, comma A, and we need this to be compared to, so versus the current label 5O. And what is this equal to? U sub A is 2 plus DAB is 2. Therefore, the label here is a 4A. And, sorry, we compare this versus the old label 5O. And because 5 is bigger than 4, or 4 is smaller than 5, therefore, we update this label 5O with the label 4A. Okay? And after labeling all the nodes that are directly connected to the current node A, we then move on to the next step. Not all nodes are permanently labeled, so we don't stop. And in that step, we are asked to look for the lowest temporarily labeled node. And in this case, the lowest temporarily labeled node is node C. So we can make node C permanent, and then we update our current node. Instead of A, no, we change it to node C. Okay? Now, for node C, what are the nodes that are directly directly connected to node C? The nodes that are directly connected to node C are O, B, and E. Okay? But because O is permanently labeled, we don't look at that anymore. Therefore, we look at B and E. Now, because E is not yet labeled, so we can quickly label E. And hopefully, it will be easy for you now to understand why the label for E is a 6C. Why 6? It is a 2 plus 4. Okay? That's why the label is a 6. Next, the label for B. What is the label for B? We are now comparing 4A. Okay? So we will compare 4A with versus what is the label of node B going through C. So it is a U sub C, that's 2, plus distance between C and B, that is 1, comma C. And this one is 3C, therefore we replace this. So we replace 4A with a 3C. Because 3 is lower than 4. And because we are done updating or giving labels to all nodes that are directly connected to C, then we check if we need to stop. No, we are not. We don't need to stop yet. So we look for the node with the lowest distance. In this case, it's B. So we make this permanent. We update this C. We are now at node B. Then we go back. In node B, we can update node D and node E because O, A, and C are now all permanently labeled nodes. No? So if you can look at the label, node O, A, and C are all permanently labeled already. So we won't look at them anymore. So D and E are currently labeled, so we will check if we need to update. So what is the label in node D going through node B? No? U sub B is 3. 3 plus 4 is a 7, which is smaller than 9. Therefore, we update this to a 7B. Okay? How about E? What is the label of node E going through B? So again, U sub B is 3 plus 3 is a 6. Because this the current label is also 6, then we can actually update this label with a distance of 6, but either we go through C or B. Okay? Next, do we stop? No, we don't stop because not all nodes are permanently labeled. So we look for the next lowest, which is E. So we make E permanent. And then we check which ones, we update this to be node E. and we check all the nodes that are directly connected to E, that are, well, currently temporary. So D and the only nodes that are temporary are D and T. So we check for D, what is the label? Currently, U sub E is 6 plus 1 is 7. Right now, the label for D is a 7B. Therefore, we can update this to a 7, comma, B slash E. What about T? U sub E is a 6 plus 7 is a 13. But because the current label for T is 12, then we don't update this because this one is shorter. Do we stop? No, we don't stop because not everything is permanent yet. So we make the current lowest permanent, which is node D, permanent. We update this D, and then we finally check and update T going through T. Now, the U sub D is a 7, and because the distance between D and T is a 5, therefore 7 plus 5, 7 plus 5 is a 12. And because the current label is also 12, then therefore we can update this to a 12, comma, A slash D. And then finally, we make this permanent. And because all the nodes are permanently labeled, then we can stop. Once the algorithm is done, we can now look for the shortest path from the origin, O, to all the other nodes. Okay? Now, just for the example's sake, let me just get the shortest path from the origin to node T, our last node here. But we will be able to do the same thing in order for us to get the shortest path from O to all the other nodes here. Okay? So how do we get the shortest path from O to T? No? How do we get the shortest path? In order to get the shortest path, it is said that we need to start from the end. So we have node T here. And according to this table, well, the distance of the shortest path from origin to T is a 12, but it has to go through A or D. So you technically have an A here or a D here. Okay? Then we moving backwards, looking at node D, the distance of the shortest path from origin to D is a 7, but it has to go through B or E. B is here. E is here. Okay? Looking at E, it has to pass through either C or B. So either it passes through B or it passes through C. C has a shortest distance of 2 and it has to go through O. B, on the other hand, it has to pass through C. So we have this. A has to pass through O. Therefore, we have node O here and it goes through C or A. And what we have here are the different shortest paths. So we have 1, 2, 3, I think 4. No? We have 4 paths that will give us the shortest path from O to T with a distance of 12. So can we check? One path is O80, so 2 plus 10, that is a 12. The next path is as OCB dt. Let's check. 2, 3, 7, 12. Okay? So that's also a 12. The next path is an O, C, B, E, D, T. Can we check? 2, 3, 6, 7, 12. Okay? And finally, the last path is an O, C, O, C, E, D, T. Can you check? 2, 6, 7, 12. So in order to get the shortest path from the origin O to all the other nodes, you do the same thing. You start from the end and then you slowly move your way backwards towards the origin.